So now the last piece that we need to add to solving equations is the fact that we can use identities to solve them. So we have all of those identities from the past couple weeks. Now they can come into play. So for example, we have sine or tangent minus sine. In this case, we have two different trig functions and we can't factor one of them apart from each other. So we need to figure out how we can get these in terms of each other and then use them. So in this one, again, they're all going to be a little bit different, but an idea that can help us is we know that tangent is equal to sine over cosine. So that at least gets it so we have sines in all of our functions. So we take tangent, we replace it with sine of theta over cosine theta minus theta equals 0. So now we have a sine in both of our terms. Now we can use the method we were using earlier today, which is we can just factor. So there's a sine in both terms. Again, if you want to change these to x's and y's, you could write this as x over y minus x equals 0. Either way, we can factor that sine out, or you can factor the x out. So if we take sine of theta, bring it out front, now we're left with 1 over cosine of theta minus 1 equals 0. Or if you want to look at this in the x and y's ways, you take that x, factor it out, you have 1 over y minus 1 equals 0. Either way, now we can separate this out. We have our two pieces, so either sine of theta equals 0 or 1 over cosine theta minus 1 equals 0. Now solve both of these separately. For sine of theta equals 0, we get 0 and pi. We're over here, add 1, and really we can change that 1 over cosine into secant. So we get secant of theta equals 1. And that's the same as where cosine equals 1, which is at 0. So in this case, that was just a repetitive answer. Your final answer would just be 0 pi. You do not need to list anything twice. In this case, just list all the answers. Okay, for this next one, we have tangent minus cotangent equals 0. So again, we can't factor anything out. However, we can rewrite these so one's in terms of the other, where we know cotangent is equal to 1 over tangent of theta. So again, use the identities, and our whole goal is to get it so we only have one trig function, or if there's multiples, we can factor them apart. So now in this case, we have tangent minus 1 over tangent equals 0. At this point, we cannot factor a tangent out, because we would just end up with a more complicated thing for that second term. However, if you ever have a trig function in the denominator of a function, then what you can do is take both sides of the equation and multiply by that trig function. Essentially, to get something out of the denominator, you multiply by it. So we can multiply everything, both sides, by tangent of theta. Go ahead and distribute that in to all pieces. So on this left side, tangent times tangent is tangent squared of theta. Tangent times 1 over tangent. The whole point is to cancel it out, just equals 1. 0 times tangent is 0. So as we multiplied both sides of the equation by the same thing, so it's still an equal equation. And now we've gotten rid of that fraction. So to reiterate, kind of the strategy we're using here is if there's a trig function in the denominator of any term, multiply both sides of the equation by that trig function in order to get it out of the denominator, to cancel it out. So now, back over here, we have tangent squared minus 1 equals 0. You can either notice this is a difference of two squares and factor it to be tangent plus 1 and tangent minus 1. Or you could add the 1 over and take a square root. But keep in mind, if you take a square root, you should have a plus or a minus on your answer. Either way, what we get here is that tangent equals plus or minus 1, negative 1, positive 1, which means our reference angle of pi over 4, and then it's going to be in all four quadrants. So 3 pi over 4, 5 pi over 4, and 7 pi over 4. Oops. And there's your final answer. Okay, so the last two use a quotient and reciprocal ID. We can also use our Pythagorean IDs. So in this case, we have sine squared theta equals 2 cosine theta plus 2. So we have two different trig functions. We need to get it so that there is only one trig function in this equation. Our key here is to notice that square on the sign. You can only use Pythagorean identities if you have something squared. So in this case, we know sine squared plus cosine squared equals 1. So if we solve that for sine squared, we get sine squared theta equals 1 minus cosine squared theta. We can replace this sine squared with 1 minus cosine squared. So we can use the Pythagorean identities, and now our whole equation only has cosines in it. There's a square in there, so this is still a quadratic, so we use our methods from earlier today. Move your terms to the other side to set it equal to 0. And we get a positive cosine squared theta plus 2 cosine squared, or cosine theta plus 1 equals 0. If you want to use u's to help yourself out, feel free. This factors to be u plus 1 and u plus 1. So separate those out. They equal 0. We don't have to write the same thing twice since it's the exact same factor. So we get cosine of theta equals -1. And that happens at pi. So we only get one answer to that equation. So keep in mind for Pythagoreans, sine squared and cosine squared go together, secant squared and tangent squared go together, and then cosecant squared and cotangent squared go together. So re-look over those Pythagorean IDs, because anytime you have a square, you'll be able to use those. Okay, last one for now. And this one, notice it's a sine and a cosine, and again, we know they relate with the Pythagorean IDs. The problem, though, is we don't have any squares. So one last method that can help you out is if you notice you have trig functions that go together with the Pythagorean IDs, you want to square both sides so that you can use the Pythagorean IDs. So the method we're using here is if you have a Pythagorean pair, but they are not squared, then you can square both sides of the equation. So square the left side, square the right side. The left side very simply just turns into sine squared of theta. The right side, keep in mind you need to FOIL this out. So 1 plus cosine times 1 plus cosine. That square does not just distribute in. And this turns into 1 plus 2 cosine of theta plus cosine squared theta. Now that we just switched this so we have squares, technically we could replace either the sine or the cosine squared. However, we have this other cosine in here, which means we're going to want to turn everything into cosine. Because if we replace the cosine squared, that's great. We'll have two sets of sine squareds. We'll still have an extra cosine to deal with. So we take this sine squared, we turn it into 1 minus cosine squared theta. Right side stays the same. And we chose the sine squared to replace because of that extra 2 cosine in there. Get everything to one side of the equation. We have 0 equals, see, the 1's go away, add the cosine squared, we have 2 cosine squared, so we have 2 cosine theta plus 2 cosine squared theta. Again, if that substitution helps, go ahead and write this as 2u plus 2u squared. You can factor a u out, or really you can factor a 2u out, and you get 1 plus u left on the inside. So we get 2 cosine of theta equals 0, or 1 plus cosine of theta equals 0. So divide the 2, subtract the 1, and use your unit circle. So we get from cosine equal to 0, that happens at pi over 2, and 3 pi over 2. And from cosine equal to -1, that happens at pi. So these are just some more methods. The whole idea is that you can use identities to help. We will continue to go through some of these tomorrow, but make sure you have all 4 of these problems written down in your notes. If you need to go back and re-watch this and watch me talk through it again while you follow your steps to try and make sense of some of these. We'll keep doing more tomorrow though.